Hey everybody, welcome to our discussion today of long-term potentiation. I will say that if you haven't read the book for this bit yet, maybe hold off on watching this video until you give it a read. This is a pretty tough concept that people often have trouble with, and it really helps to sort of read it. So that's my disclaimer. So do the work on this one or else it'll be a pretty rough time. So long-term potentiation has a lot to do with NMDA receptors. So this is a very specific receptor type that we're going to have to spend some time talking about. So touching back on some of the stuff we talked about with glutamate, the NMDA receptor is a specialized ionotropic receptor. It is a glutamate receptor subtype, right? NMDA receptors respond to glutamate. It's a specialized ionotropic receptor, meaning it contains an ion channel that controls sodium and calcium channel. So the channel is permeable to calcium and sodium. The really important thing that it's permeable to is calcium. So as I mentioned, it responds to glutamate. So glutamate is the ligand for the NMDA receptor. And normally it's blocked by a magnesium ion, right? So magnesium ion will just sort of sit in the channel and not let anything through. Glutamate alone won't remove this magnesium block and won't allow calcium to enter, right? So at its normal state, magnesium blocks the entry of calcium. The membrane must first be depolarized, which will eject the magnesium plug. So these are all words that we've talked about previously, right? If you're a little hazy, you can go back to our discussion of the action potential. Depolarization meaning sort of that change in the membrane conductance of a neuron. So it has to be sufficiently depolarized. Enough positively charged ions have to enter to depolarize the cell sufficiently to remove this magnesium block. So we can say that NMDA receptors are both ligand-gated and voltage-gated because two conditions have to be satisfied for an NMDA receptor to become permeable to calcium. 1, glutamate has to be present in the synapse, and 2, the neuron must be sufficiently depolarized to remove that magnesium ion. So we can say that NMDA receptors are coincidence detectors, right? They detect the coincidence of glutamate and the depolarization of that neuron, right? So depolarization of the neuron from any source and excitatory signaling at a specific synapse. Some of you who are listening may already be making the connection to what we talked about previously with Hebbian plasticity. The idea that we have depolarization from any source, I don't know, let's say a strong synapse, and excitatory signaling in a specific synapse, let's say our auditory weak synapse, right? So it's going to, we're getting a little bit ahead of ourselves with that, but just sort of keeping the Hebbian plasticity angle in mind. Depolarization of a neuron from any source, that depolarization is going to remove the magnesium ion, and excitatory signaling in a specific synapse, right here, that's going to allow the entry of calcium. Okay, let's also talk about the other major player in long-term potentiation, which is the AMPA receptor. The AMPA receptor is an ionotropic receptor which controls a sodium channel. There's no magnesium block here, it's just a regular ion channel that's permeable to sodium. This is activated by glutamate. It activates the cell, or it excites the cell, right? It's extremely common. Glutamate and AMPA receptors are all over the place. And these are responsible for the initial depolarization of the postsynaptic membrane, right? So if we want depolarization of a membrane, an ion channel like this one's going to be doing a lot of the work. All of the sodium coming in through AMPA receptors is going to contribute to that initial depolarization event, which will allow the ejection of magnesium from the the NMDA receptors. Okay, so now that we've established that background, let's go back to the example that we were using earlier. So if we look back, we're using the same color scheme as before. If we look back at that Hebbian plasticity lecture that we've gone through, this in red is our auditory neuron, and in blue we have our motor neuron, right? This is a weak synapse. What happens when the tone comes on is we have an action potential that arrives. When it makes its way down to the terminal buttons of this auditory neuron, it's going to cause the release of neurotransmitters. So let's have here our glutamate. It's going to be released, right? I'll orient you over here to the legend I've put over here. In light blue, we have NMDA receptors. In dark blue, we have AMPA receptors. The blue ligand is glutamate. Yellow is calcium. Purple is sodium. And this grayish brown color is magnesium. So we have a magnesium block in place right here in our NMDA receptor. So what happens is that action potential comes on down. Out comes the glutamate. It binds to whatever receptors it can reach. So it's going to open up an AMPA receptor, which is going to allow a little bit of sodium to flow through. Not a lot, but a little bit. We cannot really activate this NMDA receptor because the magnesium block is still in place. There's not been enough depolarization of this motor neuron. So this is just basically you in your pre-learning state, right? You hear auditory neuron, you don't blink. You hear a sound in your environment, your auditory neuron fires, but you don't blink. You have weak depolarization of the postsynaptic neuron, and thus no action potential takes place. Okay, what about the synapse between your somatosensory neuron and your motor neuron? So in this instance, we have a little puff of air coming in, and when your somatosensory neuron detects that, it fires an action potential, which will cause the release of glutamate from this terminal button. This will come out, bind to all of these AMPA receptors, as well as the NMDA receptor. So what's going to happen here? All those open. A lot of sodium flies in. That's going to cause a strong amount of depolarization. In fact, the depolarization is strong enough to remove this magnesium ion. What happens next is calcium and sodium are able to enter via the NMDA receptor, right? This will result in an action potential taking place in the motor neuron. Right, so we saw strong depolarization, right? All of these AMPA receptors causing depolarization, which is enough to cause an action potential. Okay, this is the critical piece right here. We're going to bring everything together. So in green, we have our somatosensory neuron. Red, we have our auditory neuron. And we have two different dendrites of our motor neuron, right? This is the same neuron, right? In blue here. These are two processes from the same neuron. So what happens is we have our action potential arrive in our somatosensory neuron. It's going to do just what we saw before, where it's going to cause a depolarization event. In goes the sodium, out goes the magnesium, and then our NMDA receptor channel opens, and in goes the calcium and the sodium. Here's the interesting bit. So we have the spreading depolarization as part of the action potential, makes its way down from this dendrite, and that will come in to be important in just a moment. So here in the meantime, we have our auditory neuron, and action potential arrives here, right around the same time. Out goes our glutamate, binds to our AMPA and NMDA receptors. So in goes our sodium. But what's this? Here comes that spreading depolarization, right? The depolarization from this synapse affects this synapse. It's going to cause the ejection of that magnesium ion, which is going to allow this NMDA receptor to allow some sodium and, importantly, some calcium to come through. So this is the supercritical bit that sort of ties everything back together, right? The fact that the depolarization here at the strong synapse is going to cause some depolarization at the weak synapse. And if the auditory neuron is firing at around the same time that the somatosensory neuron is, it can benefit from this depolarized synapse, right? That's the reason, one of the reasons why this type of learning requires the CS and the US to be so close together in time, right? In order to learn that the air puff is predicted by the tone, they have to happen nearly at the same time. So this somatosensory neuron depolarization event is going to prime this synapse here for long-term potentiation. Okay, let's zoom in a little bit further at that weak synapse and look at exactly what's happening. So here we have glutamate binding to the NMDA receptor, which is going to allow calcium in. And we're going to do kind of an abbreviated version of the cascade that happens following LTP. There's a lot more stuff that happens that's kind of offshoots of this cascade, but we're just going to hit the main, most important bits. So the entry of calcium into this postsynaptic neuron is going to activate two very important enzymes, which are PKC, which is protein kinase C, and CAM kinase 2. So these enzymes are important for a lot of changes that will take place inside the cell, which will result in the trafficking of additional AMPA receptors into the synapse. Remember, AMPA receptors are these really, really ubiquitous glutamate-sensitive ion channels that allow sodium in. So, right, they are excitatory ion channels that respond to glutamate. So PKC and CAM kinase 2 only remain active at high levels following calcium entry for a brief period of time. In addition to the actions they perform with the trafficking AMPA receptors, they also activate a different enzyme called PKMZ. So protein kinase M-zeta, or PKMZ or PKM-zeta. This is an enzyme that's really, really important for maintaining LTP after the initial event has taken place. So maintaining the changes in plasticity in this synapse. PKMZ is really important for that. So the nice thing is PKMZ is capable of keeping itself phosphorylated or in an active state. So once PKMZ is activated, it continues to keep itself active for a relatively long time, keeping the changes that have taken place as a result of LTP constant. So here we have our auditory synapse after learning has taken place, after long-term potentiation has taken place. So what do we see? Tone comes on, action potential arrives. This time, lots of glutamate's released, binds to AMPA receptors, sodium in, magnesium out, channel opens, in comes calcium and sodium, producing an action potential, right? So this has changed. This neuron has changed. So because of these increased amount of AMPA receptors, and also some other mechanisms that we'll talk about, like increased release of glutamate via retrograde signaling, we see a action potential takes place where there was no action potential before, right? So we've learned that the tone predicts the occurrence of the puff. So now when the tone comes on, we blink. And that's what it looks like in terms of changes in your cells, right? We have more AMPA receptors trafficking into the synapse. Now it's more sensitive to glutamate. So when glutamate does get released from the terminal, it has more places to bind to. It's going to open up more channels. It's going to cause a larger depolarization event. In fact, depolarization event is now to cause an action potential all on its own. So now after learning has taken place, we have LTP initiated. Now the auditory neuron is capable of driving activity at this motor neuron all on its own. So in addition to the changes in terms of receptors being trafficked to the synapse, they're actually real morphological changes. So we have these things called dendritic spines. Dendritic spines are basically just little protrusions on your dendrites, which are the portion of the dendrite that forms a synapse with the terminal button of the presynaptic neuron, right? So it's kind of like a receiving site for information, right? It's the receiving portion of the synapse. And we see growth of dendritic spines after long-term potentiation. So not only are there sort of these neurochemical changes, but there are morphological changes, right? The actual size and shape of your neuron's receptive areas grows as a result of learning. So let's look at this again in terms of some static images, right? We looked through things with animations before. Let's look at some static diagrams that might be a little bit easier to study. So glutamate's released from the presynaptic terminal. It crosses and binds to NMDA receptors and AMPA receptors. So this postsynaptic neuron is in a primed state, so the neuron has been sufficiently depolarized. So this NMDA receptor channel is now permeable to both calcium and sodium. So calcium is the important bit because calcium is what we call a second messenger. It's capable of sending signals within the cell. So calcium comes in and it activates a cascade of a bunch of activity within the cell. Among those things, we're really interested in CAM kinase 2, as we mentioned, and other protein kinases, which are going to lead to the insertion of additional AMPA receptors. And again, those additional AMPA receptors are a big piece of the change that supports long-term potentiation, right? Because those extra excitatory ion channels are there, the cell is going to now have a potentiated response to excitatory neurotransmission. Okay, let's just completely verbally sum up LTP. So this is the way you might be able to describe it to a friend who's interested in plasticity. So NMDA receptor activation allows calcium to enter. So you need to be able to understand everything that leads up to NMDA receptor activation first, right? So NMDA receptors, as we mentioned at some length, are coincidence detectors, right? They detect 1, depolarization of the neuron, and 2, presence of glutamate at that synapse. So if those two conditions are met, NMDA receptors are activated and allow calcium to enter. So depolarization and glutamate signaling are both needed for that to take place. So once calcium is in, it does its super important job of activating a signaling cascade. CAMK2 and PKC are among the enzymes that we're going to be talking about. These are the most important that we're mentioning, but there are others. So these, among other things, traffic additional AMPA receptors into the synapse. Remember, AMPA receptors being that sort of ubiquitous workhorse excitatory receptor that responds to glutamate. That means that there's going to be more receptors to respond to glutamate. We also have some retrograde signaling that takes place that allows the presynaptic neuron to actually release more glutamate. So not only do we have more excitatory glutamate receptors, we also have more glutamate being released from the presynaptic neuron. If we have continued calcium signaling, so this takes place multiple times, calcium continues to stick around and allows for the activation of PKM-zeta, which is a self-sustaining signaling molecule that will maintain these changes for the life of the memory. So we need PKMZ activation to keep LTP active for a long-term memory. In fact, if we block the activation of PKMZ, the memory is lost. So this is absolutely necessary for long-term potentiation to take place. Okay, I know that's kind of a lot of information, but do your best with it. We will talk about this in our synchronous session, and also I encourage you to read your book. It does a great job describing this. All right, so that's it for LTP. I'll see you next time.